Physics students, this is Mr. Evely speaking to you. This is just a short video to wrap up our chapter on electric circuits and the beginnings, anyway, of electric circuits. One thing I forgot to do the other day was an example about current density. So let me back up just a little bit and let's take a look at that. Here's the example on the PowerPoint. It's actually problem number 11 from the text. It says the magnitude JR of the current density in a certain cylindrical wire was given as a function of radial distance from the wire's center, center of the wire's cross section as JR equals BR. In other words, the current density varies with the radius. B is just a constant, and they give it to you as 2.00 times 10 to the 5th amps per cubic meter. And it says this function applies out to the wire's radius of 2 millimeters. How much current is contained within the width of a thin ring concentric to the wire if the ring has a radial width of 10 micrometers and a radial distance of 1.2 millimeters. Okay, so let's translate this into something that kind of makes sense. Okay, so what they're saying here is that we've got a wire, and that current density varies as you move out. So in other words, you've got greater current density in the exterior regions, lesser current density toward the center. So J varies as a function of R. Now, if we blow this up a little bit, look at the cross-section a little bit bigger. What they want to know is how much current is going through a region that looks like this. It's kind of a thin cylinder that's concentric to the cross-section of the wire. So, how are we going to do this? How are we going to figure out how much current is going through here? A couple of things they tell us. They tell us that this constant B is 2 times 10 to the 5th amps per cubic meter. It's just the units they need to use in order to make it work out. They tell us that this thin ring has a radius of 0.00120 meters. So it's 1.2 millimeters. I converted it to meters. They also tell us that the thickness of this ring is 10 micrometers. Okay, so I'm going to call that dr. So looking at in meters would be 10.0 times 10 to the minus 6 meters. Now, of course, our definition of current density is some kind of current per unit area, but the problem is that applies to a uniform current density. This current density is not uniform. So what we have to do is kind of look at the integral of this puppy. So in your notes, we have the definition of current equals current density, the integral of current density with respect to area. All right, so for this particular problem, all we want is the current running through that ring. In other words, we want the little bit of the total current that's there. Now, if we're looking for di, J we can replace with B times R. A we can replace with the area of this thin ring. So the area of that thin ring, if we take that thin ring and we cut it and we lay it flat, it's going to be 2 pi r times dr. So I'm going to take dA here, and I'm going to write it as 2 pi r dr. So that little bit of current that we're looking for is going to be 2 pi b r squared dr. So our last step is to put the numbers in and figure it out. So I've got di equal to 2 pi b, 2 times 10 to the fifth. That's amps per cubic meter, weird units, times r squared. So I've got 0.00120 squared, and that's in meters. And then I've got dr, my little chunk of radius, which is 10 times 10 to the minus 6 meters. So this little tiny bit of current is 1.81 times 10 to the negative fifth amps, or 18.1 microamps. That's pretty tiny. All right, so that's a fairly challenging problem using differentials and current density to figure out the current through a tiny bit of wire. Kind of a strange example. Okay, our topic for yesterday was resistance and resistivity. So as a quick review, remember, Ohm's law says I equals V over R. So we define resistance as V over I. In other words, it's the voltage required to cause 1 amp of current to go through the item, the piece of metal or resistor or whatever it is. We said then resistance has units of volts per amp, which is an ohm. Now, that is a property of the item that you place in the circuit, whether it's a light bulb or a resistor or even a wire. But the material, certain materials like copper and iron and other conductors have something called resistivity. And resistivity doesn't depend on how much of the stuff you have. It just depends on the material substance it's made of. So in other words, just like density, density doesn't depend on how much copper you have. The density of copper is the same, no matter how big a piece you have, because we measure it in kilograms per cubic meter or grams per cubic centimeter. It's a characteristic property. In other words, knowing the density of a substance, you can go back into a table and maybe even identify that substance. Resistivity is the same way. Resistivity, we use the Greek letter rho, and it's equal to the electric field through the piece of metal divided by the current density. And this should be in your notes already, but this is just a quick review. Again, the units of this thing are going to be volts per meter on top and amps per square meter on the bottom. So if we cancel out some of these guys and rearrange, we get volts per amp times meters, which is an ohm meter. So ohm meters are the units of resistivity. The opposite of resistivity is conductivity. And conductivity is just the reciprocal of resistivity. So if they ever ask for the conductivity instead of the resistivity, you just flip it. Okay? Now, if you go to a table and you look up the resistivity of a metal, And then you have a particular piece of metal that you want to put into a circuit, be it a wire, resistor, light bulb, or whatever. We can calculate the resistance of it, knowing the resistivity and some of the properties of that piece of metal. So here we go. Now, we said resistivity is E over J, but we know from the previous chapter that E is equal to V over L. So in other words, you have a piece of metal here. You want to know its resistance. If you put it in an electric circuit, L would be the length. The voltage is going to be the potential difference across the piece of metal. But again, because of tradition, we don't say delta V in the equation. We say V. So don't get confused. Okay, so this is just another form of V equals ED because the electric field inside the metal is uniform. Okay, J is just I over A. So we're going to assume a uniform current for a moment. So P can be rewritten as V over L divided by I over area. Okay, quick rearrangement of this says that VA over IL is resistivity. But remember, V over I is resistance. So we can write this as resistance times the ratio of area over length. Or better yet, we could say the resistance of a piece of metal or whatever we're looking at is its resistivity times its length divided by the area. Now this makes a strange sort of sense because the bigger the resistivity of the metal, the bigger the resistance. The longer the length of the metal, the more chances electrons passing through it will run into atoms. So the greater the length, the greater the resistance. The bigger the area, the less resistance. So again, if you think of a water pipe, something with a large cross-sectional area allows water to flow through it very easily. Something with a small cross-sectional area, like a tube, it's much more difficult to get current to flow through it, or in this case, water to flow through it, if you think of the analogy. So if you need to get 5 gallons per second to travel from one place to another, you'd want to pick something with a big cross-section rather than something with a small cross-section because it's just a lot easier. Okay? So when you're looking at electric circuits, a larger cross-section creates less resistance for the current to flow. So if you have something like a space heater or an air conditioner or something that requires lots of current, you want to use a big, thick wire when you plug it in. And you notice most of those devices have really thick wires to reduce the resistance because there's a great amount of current passing through them. So let's take a look at an example. All right, let's see if this thing will let me do that. Okay. Calculate the resistance of one of our Pascal cart masses. So these black masses that we use all the time when we want to weigh down our carts are just big chunks of iron. And the dimensions of that chunk of iron, it's got a length of about 13 centimeters. The area we can get, because these little guys are 2 centimeters by 2.5 centimeters. Okay, so suppose you want to find the resistance if you were to put one of these puppies into a circuit, I don't know why you'd want to, but let's say you did. Okay, once again, resistance is rho L over A. Now, rho we can get going to page 689 in your textbook and looking up the resistivity of iron. Now, resistivity of iron is 9.68 times 10 to the negative 8 ohm meters. All right? So, it's pretty straightforward. We're going to say 9.68 times 10 to the negative 8 ohm meters times a length of 0.13 meters times an area of, now here we have to be careful, it's 2.0 centimeters times 2.5 centimeters. So we've got 5.0 square centimeters of area. A quick-o change-o tells us that square centimeters and square meters, 1 square meter is going to be 10,000 square centimeters. So we have to say 0.00050 square meters, if I did that right. That's better. Okay, so a quick calculation, 9.68 times 10 to the negative 8 times 0.13 times 0.0005. So we get a very small resistance for this puppy. I've got 6.3 times 10 to the minus 12 ohms. So small resistance as you'd expect. If it's iron and it has a huge cross-sectional area, you'd expect the resistance to be pretty large. Okay, onward. Ohm's law we had last year. We normally call it V equals IR. But again, I really like I equals V over R because it kind of makes sense. If you want current to pass through something, you want a huge potential difference. The bigger the potential difference, the bigger the current. The resistance, however, tends to hold back the current. So we put resistance on the bottom. The bigger the resistance, the less current passing through. Okay, many circuit elements obey Ohm's law. That's something that you saw last year, so I'm going to move on. Power. Again, from last year, power is very easy to calculate. It's just I times V. Because remember, I is the number of the amount of charge passing through the circuit per unit time. And voltage, or potential difference, is the amount of energy or work. So if we say energy, for example, per unit time. I beg your pardon. Energy per coulomb of charge. Sorry about that. So if you do a quick-o cancellation here, we get energy or work per unit time. So it makes sense that power is current times voltage. However, in an electric circuit, if you have a resistor, what happens is that electrical energy in the resistor is converted to heat. So to figure out how much heat, how much energy is being converted to heat, we can use this equation, but not exactly in this form. What we need to do is we need to say, wait, V equals IR, so the equation becomes I times IR, or I squared R. This equation we use for dissipative effects. So when we're figuring out how much electrical energy is being converted to heat energy, I squared R is the one we want to use. Again, we used this last year, but what it says is that the bigger the current through the wire, the more electrical energy, or the quicker electrical energy is to be converted to heat. That's why wires with high currents running through them, like the elements of a stove, or even the power cord of some major appliances, get very warm because of the large currents passing through them. The bigger the current, the more energy loss. That's why when we transfer electrical energy from, say, a power plant to your home, we use extremely high voltages to keep the current way down. If the current is really low, there's much less heat loss, or sorry, electrical energy lost to heat as it passes through the wires outdoors before it reaches your home. Okay? The book also points out that we can rearrange this thing. In other words, we can take I and say, hey, if I is V over R, to do a replacement here, and we get power is V squared over R. Okay, so lots of wonderful equations showing up in the last couple sections, but nothing too terrible. Okay? All right. There we go. All right. So it says a 240 electrical potential difference is applied across the spiral-resistive heating element on an electric stove. If the heating element dissipates 700 watts during operation, what's the resistance? All right. So we would say to ourselves, okay, we've got a V of 240, and power is 700 watts. Okay? And so we would like to know what R is. So just like a few seconds ago, we'd say, hey, power is V squared over R. And this becomes a pretty simple situation. Just take the potential difference. Oops, sorry, that's 240 volts. Divided by 700 watts. Okay, so these problems aren't too terrible. A potential difference of 1.20 volts will be applied to a 33.0 meter length of 18 gauge copper wire, given the diameter. Calculate the rate at which thermal energy will appear in the wire. We've got V equals 1.20 volts applied to a 33 meter length. Okay, our diameter is 0.0400 inches. Oh, lovely. So that means a radius of 0.0200 inches. Okay. So how do we get the rate at which thermal energy, that's power, passes through the wire? Well, I think what we're going to do is a V squared over R again. Okay, we've got V. How do we get R? Okay, remember R is equal to resistivity times length divided by area. So when you solve this problem, I would use the length in the equation, the resistivity of copper, we could look up. Resistivity of copper is 1.69 times 10 to the 8. -8. And of course, the units are ohm meters. All right, so our biggest hurdle here is getting the area. Of course, we need to do a quick change-o on that, inches to centimeters. Oops, let's do that to the radius. Sorry about that. So 1 inch is 2.54 centimeters. Then we might as well change it to meters. Okay? And I think you know what to do from here. The area can be changed to pi r squared. Once we know the radius, we know the resistivity, we know the length, we've got resistance. Once we have resistance, we're home free. All right, so let's see if I can do this without embarrassing myself. 0.02 times 2.54 divided by 100 is 5.08 times 10 to the negative 4. And that will be in meters. All right, last step. Second to last step, get the resistance, which is 1.69 times 10 to the negative 8 ohm meters, times the length, which is 33 meters, divided by pi times r squared. All right. So 1.69 times 10 to the negative 8 times 33 divided by previous answer squared divided by pi. So we're getting a resistance of about 0.688. Okay, so the power we can get, and I think you can answer it from here, 1.20 volts on top. Make sure you square it. Resistance on the bottom, 0.688 ohms. We get 2.09 watts. All right, that concludes my presentation for today. You guys take care. I will see you on Monday. Get the assignment done and treat the sub well. Thanks.